Welcome to my talk. I'm Keita Emura from NCT Japan. I'd like to talk about my paper entitled Generic Construction of Public Key Authenticated Encryption with Keyword Search Revisited, Stronger Security and Efficient Construction. This is a summary of my talk. Public key encryption with keyword search (PEKS) is a searchable encryption in a public key setting. As a security requirement, no information of keyword is leaked from ciphertext. However, in PEKS, information of keyword is leaked from trapdoors. To solve this issue, public key authenticated encryption with keyword search (PAEKS) was proposed by Huang and Li in 2017. PAEKS provides a trapdoor privacy, which means that no information of keyword is leaked from trapdoors. And recently, generic construction was proposed by Liu et al. At ASIACCS 2022. So, in this paper, we propose a new generic construction of PAEKS. Our construction is more efficient than Liu et al. Construction. Moreover, we consider a stronger security model than that of Liu et al. We also highlight several issues associated with the Liu et al. Construction. For example, their construction does not satisfy the consistency. We should note that Liu et al. Have updated the ePrint paper in accordance with our analysis. Especially, they introduced a random oracle. First, I'd like to introduce a public key encryption with keyword search (PEKS). There are three entities: a sender, a server, and a receiver. First, the receiver generates a public key and secret key, and the sender encrypts some keyword prime, by using the public key. And the CT-PEKS is a ciphertext. And the sender sends this ciphertext to the server, and the receiver generates a trapdoor by using a secret key for some keyword, and send the trapdoor to the server. And then the server runs the test algorithm. In accordance with the result of the test algorithm, server returns a ciphertext as the answer of the search query. And PEKS requires a correctness, which means that the test algorithm returns 1 if keyword prime equals keyword. And moreover, consistency is also required, which means that the test algorithm outputs 0 if keyword prime and keyword are different. In addition, the no information of keyword is leaked from ciphertext here. But in PEKS, information of keyword may be leaked from the trapdoor. In order to show the information leakage, I'd like to introduce a keyword guessing attack. Now, adversary has some trapdoor and wants to know which keyword is associated to this trapdoor. First, the adversary chooses a keyword and encrypts this keyword. And PEKS is a public key setting, so anyone can generate a ciphertext of any keyword. And then the adversary can check whether this trapdoor is associated to the keyword or not by the test algorithm. So, information of keyword is leaked from trapdoor in PEKS. To solve this issue, public key authenticated encryption with keyword search PAEKS was proposed by Huang and Li. And in PAEKS, a sender also has a public key and secret key pair like this. And the encryption algorithm takes sender secret key as input in addition to the public key of the receiver like this here. And this setting potentially prevents the keyword guessing attacks because ciphertext is generated by secret key holders. And the trapdoor is associated with not only a keyword but also a sender like this. So the receiver indicates a sender by using the public key of the sender for generating the trapdoor. And as in PEKS, correctness requires that the test algorithm outputs 1 if keyword prime equals keyword. And consistency requires that the test algorithm outputs 0 if keyword prime does not equal to keyword. So next I would like to show that this definition should be improved in accordance with the functionality of PAEKS. Let me introduce our correctness and consistency definitions. So in this paper we consider multi-senders. There are n senders, and each sender has a public key and a secret key. And let the ith sender generate a ciphertext by using the ith sender's secret key, like this. And let a trapdoor be generated by indicating the jth sender by using the jth sender's public key, like this. So here, correctness requires that the test algorithm outputs 1 if keyword prime equals keyword and I equals to j. Moreover, consistency requires that the test algorithm outputs 0 if keyword prime and I does not equal to keyword and j. So this relation captures the case that the keyword prime equals keyword, but the I does not equal to j. So in the PAEKS, a trapdoor is associated with not only a keyword but also a sender. So we should consider this case. Next, we introduced two security notions, IND-CKA and IND-IKGA. So IND-CKA guarantees that no information of keyword is leaked from ciphertext as in PEKS. So the challenge ciphertext is computed by keyword as the B. B is either 0 or 1. And IND-IKGA guarantees that no information of keyword is leaked from trapdoors. So the challenge trapdoor is computed by the keyword as the B. B is either 0 or 1. And now, adversary is allowed to access two oracles, trapdoor oracles and ciphertext oracle. And the trapdoor oracle takes the keyword and some index I and generates a trapdoor for this keyword and by using the ith sender's public key. And this is the restriction that keyword I does not equal to the challenge ones. And ciphertext oracle takes keyword and index I as input and compute the ciphertext. In the IND-CKA game, there is no restriction, but in the IKGA, the keyword and I does not equal to the challenge one. And in our security definitions, the challenge keywords, keyword 0 star and keyword 1 star can be input to the oracles as in the Qin-Cui-Zheng-Zheng definition. But the Liu et al. Did not consider these stronger security notions, so our scheme is more secure in this sense. Next, let me introduce Liu et al. Generic construction. They employed the word-independent smooth projective hash functions and PEKS. So first, I'd like to introduce word-independent smooth projective hash functions. So there are two key generation algorithms, hash keygen and projection keygen. This is the hashing key and this is the projection key. So alpha is a language parameter, and in the Liu et al. And our constructions, the alpha is a public key of a public key encryption scheme. And word independent means that this projection key generation algorithm does not take a word as input. So there are two hash algorithms. One is a hash that takes a word as input and outputs as some hash value. And the second one is a projection hash algorithm that takes witness in addition to the word as input and generates some hash value pH. As a correctness requirement, if the word and witness satisfy some relation, in this sense, this word belongs to some set. In the Liu et al. And our constructions, this set is a ciphertext of 0. And then these two hash values are the same with overhovering probability. And the second one is with smoothness. If the word belongs to this set, which means that set of ciphertext whose decryption result is 1, then H is statistically close to random. So next, I'd like to introduce a core idea of Liu et al. Generic construction. And they employed a cut by contention PEKS construction and employed word-independent smooth projective hash functions for languages of ciphertext. So they are sender and receiver, and language parameter is a public key of some PK scheme. So sender generates a hashing key and prediction key, and alpha is a public key. And the receiver also generates a hashing key and projection key. And this projection key is a public key of each sender and receiver. And password is encrypted by using this public key and let C be a ciphertext. And C prime is also a ciphertext of some password. Here the word is a ciphertext C and C prime, and the witness is password. So sender can compute this value, and the receiver also can compute this value. So due to the correctness of the smooth project hash function, this value and this value are the same, and this value and this value also the same. So these two values are the same. Since the password is not shared in advance in PAEKS, so the Liu et al. Modified the cut by contention construction. So the C and C prime is a ciphertext of 0, and row S and row R is the randomness. So the witness is now the randomness, and this values also changed. By using this key, shared key is defined, and keyword is converted to the extended keyword by using this shared key and hash function. And the receiver also converts this keyword to the extended keyword, and the remaining part is the same as PEKS. And the trapdoor for some keyword is a trapdoor for this extended keyword. And encryption is also a ciphertext of this extended keyword. So in this construction, there are mainly two issues. First one is the information of keyword is leaked from this extended keyword, even if this hash function is one way. Moreover, even if this hash function is collision resistant, there exists some keyword and keyword prime such that the extended keywords are the same, but the keyword does not equal to keyword prime. This violates the consistency. So later, the Liu et al. Updated their paper, and now HF is a random oracle. So these issues may be solved. Next, we introduce our generic construction. We point out that the receiver does not have to prove the possession of the witness in the PAEKS context. So we remove this part and also this part. And then the shared key is defined like this. So here row S is the witness, and this is the security key of the sender. And for computing this value, sender needs to use secret key row S, but for computing this value, receiver just use the public key of the sender C like this. Moreover, we employ the pseudorandom function for deriving extended keywords. So the extended keyword is the pseudorandom value computed by this pseudorandom function. and the remaining part is the same as PEKS. Next, we briefly explain the security of our generic construction. Intuitively, the extended keyword is random. If PK is IND-CKA secure, smooth project hash function provides correctness and smoothness, and PRF is pseudo-random. So for encryption, usually the secret key of the sender, (s), is used for computing this hash value, and we can modify this computation like this. Here, the witness (s) is not required. This modification does not affect the security owing to the correctness of some projective hash function. And next, this ciphertext C is changed to the encryption v1, and this modification is indistinguishable owing to the IND-CKA security of the underlying PKE. In the smooth project hash function context, this case, the C belongs to this set, and now after modifying the ciphertext, now our word, the ciphertext belongs to this set. So now we can utilize the smoothness of the smooth project hash function. So instead of computing this value, we can randomly choose H. So this modification is indistinguishable owing to the smoothness of smooth project hash function. So now pseudo-random function can be random function because the key H is now random. So instead of computing this extended keyword using pseudo-random function, we can randomly choose this extended keyword. This modification is indistinguishable owing to the pseudo-randomness of PRF. So finally, we can say that this extended keyword is random. So extended keyword is random if keyword I does not equal to keyword primed J, then we can say that its extended keywords are different. So our construction provides a computational consistency if the underlying PEKS provides computational consistency in addition to PKE smooth project hash function PRF as above. Next, we show that no information of keyword is leaked from ciphertext. In our encryption algorithm, first keyword is converted into the extended keyword by using pseudo-random functions and computes the PEKS ciphertext. So in our construction, PAEKS ciphertext for keyword is PEKS ciphertext for extended keyword. So if the PEKS provides IND-CKA security, which means that no information of this extended keyword is leaked from this PEKS ciphertext, and then our construction is also IND-CKA secure. Of course, in the security proof, we need to show that the oracles in the PEKS experiment should be simulated by oracle in the PEKS experiment. So please check my paper for details. So next, we show that no information of keyword is leaked from the trapdoor. So as in the inclusion algorithm, the keyword is converted into the extended keyword by using the pseudo-random function, and the trapdoor is computed by using this extended keyword, like this. So the PAEKS trapdoor for keyword and sender's public key equals the PEKS trapdoor for extended keyword derived by the sender's public key. So as mentioned before, the trapdoor may leak the information of here extended keyword, but extended keyword is now indistinguishable from random. So this is enough for showing that our construction is IND-IKGA secure. As a remark, that we do not consider multi-trapdoor indistinguishability. In this setting, adversary is allowed to obtain the trapdoors for the challenge keyword and the challenge sender's public key. So please check our paper for detail. Next, we explain that our generic construction is feasible, especially from lattices. And word-independent smooth projective hash function for in the CPU ciphertext had been proposed by Benhammer et al. And here the underlying PK scheme is a CPA variant of Michancho PICAT PKE. And for PEKS, Abdullah et al. Shows that the anonymous IB implies PEKS, and basically the lattice-based IB is anonymous. So we can employ any lattice-based IB as the underlying IB scheme, and then we can construct the PEKS. So this means that our generic construction is feasible. This is the conclusion of my talk. In this paper, we propose a new generic construction of PAEKS. Our construction is more efficient than Liu et al.'s construction. So Liu et al.'s construction employed two smooth projective hash functions, but we just employed one smooth projective hash function. We also consider a strong security model that Liu et al. Did not consider. So in accordance with our security analysis, Liu et al. Has updated their paper, and now their construction requires random oracle. But in our construction, no random oracle is required. This is the end of my talk. Thank you for your attention.